welcome to GemChem. Now today's video is on understanding symmetry in inorganic molecules part 5 video, and already 4 videos are uploaded in channel on symmetry. You can watch it. I will give the link in the description box as well as the I button present above this video. And if you're new to GemChem, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. So in this video we are going to deal with how to convert the symmetry elements which we have already learned into a matrix form. Now since it is a 3 cross 3 matrix, so always remember when we are considering 3 cross 3 matrix, the changes in the coordinate of x, y and z in the 3-dimensional space will be denoted in the diagonal elements, and all the other elements will remain as zeros. So when we talk about our first symmetry element, that is identity operation, none of the coordinates change, right? So we know that E cap, that is the function E, has the coordinates. If we operate the E operation on x, y, z, then we will get back x, y, z. So the matrix for this E operation is actually 1, 0, 0, 0, 1, 0, and this is 0, 0, 1. So when you are seeing that x is becoming x, the coordinate becomes 1. But if you see that x is becoming minus x, that is an element which is present here. Suppose its coordinate is x. Now after the symmetry operation it comes here. Its coordinate will remain as x, but when it comes to this side, then its coordinate becomes minus x. So this is how we are going to see the transformations of different symmetry element, then converted to the matrix form. Now second one is our another symmetry element, that is C2x. Now this is your coordinate axes. This is x, this is y, and this is z. Now you have here an object which has a coordinate of x, y and z. Now when you rotate along this axis C2x, your x remains as it is, but what happens is that your y coordinate becomes the opposite one, that is minus y, and your z coordinate becomes minus z. So finally the 3 coordinates of x, y, z on operating by C2x forms x minus y and minus z, and from here the matrix comes to be as 1, 0, 0, 0, minus 1, 0, 0, 0, minus 1. Now let us see for the next one, which is our C2y. So when we are talking about the C2y axis, the same coordinates are being taken. Which one will remain same? Yes, the y coordinate will remain same, and the others, which is x and z, will change. So finally we get this one, that is minus x, y remains as it is, and your minus z. So the matrix becomes minus 1, 0, 0. Here you have 0, 1, 0, 0, 0, minus 1. Same if we go for C2z, then if operated on x, y, z coordinate, it becomes minus x, minus y and only z. Your matrix is minus 1, 0, 0, 0, minus 1, 0, and the last 0, 0, 1. This will be 1. So this is our final matrix, and we have already now seen or obtained the matrix for C2x, C2y and C2z. Now we are going to see for the next one, which is our I. When we talk about the I, it causes the change from all directions. So a point placed at x, y, z coordinate will be completely transferred into an equal and opposite back direction. So the point will come somewhat like this and all the coordinates will become negative. As a result, the matrix representation for I is actually -1, 0, 0, 0, -1, 0, 0, 0, -1. So this is how I can be represented using 3 cross 3 matrix. Next we are going to see the sigma operations. So in case of sigma x, y. Now since we are considering the x, y plane as the sigma, so if you consider this as x, this as y, so a point placed here towards you will be reflected at the back. That is, if this is x, y, z coordinate, it is present towards us, this is z. So when reflection occurs, this point will come here. So it will become x, y and z becomes negative. So for this case, we can see that x, y remains constant, only the other one changes. But in case of C2x, we saw that x remains constant, other two changes. So the matrix becomes 1, 0, 0, 0, 1, 0, 0, 0, -1. So let us quickly write the matrix of sigma yz directly. So the matrix for sigma yz will be y and z will remain constant and your x will change. So this will be -1, 0, 0, 0, 1, 0, 0, 0, 1. And for sigma zx, similarly you can see that only y will change. So 1, 0, 0, 0, -1, 0, 0, 0, 1. Right? So these were the simplest operations which we have now seen in the matrix representation. Now we are going to see how can we multiply these matrices. So one of the multiplications which I will show you is, see here, C2z into sigma xy. So what are the matrix? Start writing -1, 0, 0, 0, -1, 0, 0, 0, 1. And for sigma xy it is 1, 0, 0, 0, 1, 0, 0, 0, -1. So now on multiplying, what we get is -1, 0, 0, 0, -1, 0, 0, 0, -1. Now whose matrix is this one? Let us go back and see. Now if you observe, for I the matrix is this one. So we have obtained this as the I. This is our I. I is also noted as S2. Right? So in this way you can multiply different operations to get another different operation. Now you can try doing C2z into sigma vxz and let me know in the comment what operation do you get from here. Right? Now after this we are going to see what are the general formulas for the matrix in case of Cn axis. So Cn axis when we are considering, in that case your matrix is cos 2 pi by n, next element sine 2 pi by n, 0, here minus sine 2 pi by n, cos 2 pi by n, 0, 0, 0, 1. And when we are considering the general matrix for Sn axis, it will be cos 2 pi by n. Next we have our sine 2 pi by n, 0, minus sine 2 pi by n, cos 2 pi by n 0, 0, 0, minus 1. So the change comes in this block where we are getting a minus 1, but in previous case it was plus 1. So here ends the topic where we had converted the symmetry elements into the matrix. In the next video, we are going to see how to prepare group multiplication tables using the symmetry elements. So hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe and comment.